Assalamu alaikum. I hope that you are all fine. In this part, we are going to study the RC circuit in the case of charging and discharging of a capacitor. Now we are going to start with studying the charging process in an RC circuit. For this aim, we've constructed the following circuit, which contains a capacitor, a resistor connected in series across a generator. To study the value of the voltage across the capacitor, we've connected a voltmeter in parallel across the capacitor, and in order to study the value of the current inside the circuit throughout the charging process, we've connected an ammeter which is in series with the resistor inside the circuit. We are going now to see the graph showing the variation of the potential difference or the voltage across the capacitor as a function of time, and the other one, which is the graph showing the variation of the current inside the circuit as a function of time. I'm going to start the charging process, and you are going to see the variation of the potential difference or the voltage and the current. Notice that the voltage of the capacitor is increasing, and it is starting from 0. It is not increasing linearly, it is increasing exponentially, and the exponential function is a new concept for you, and you are going to learn it in math. What is remarkable about this exponential function is that it increases faster in the beginning and it slows down at the end of the increase or at the end of the process. Notice here that the voltage of the capacitor initially is equal to 0, and at the end of the charging process, it is equal to the EMF of the generator, which is in this case equal to 5 volts. So the voltage as a function of time is an exponential function which is increasing from 0 until it reaches approximately 5, which is the maximum voltage of the capacitor. Whereas the current, as we know that the current decreases in the charging process, in this case, we can see from the graph that the initial value of the current is the maximum value, which is in this case approximately equal to 32 microampere. It decreases exponentially, that means faster at the beginning, and then it decreases but in a slower way until it reaches 0 at the end of the charging process. So the current decreases exponentially, and the potential difference or the voltage across the capacitor increases exponentially. Time constant of an RC circuit is a new and very important definition. Time constant, which is denoted by this letter, pronounced tau, is defined by the time needed to perform 63% of the charging or the discharging process. For example, if the maximum voltage of the capacitor is equal to 100 volts, then at time t is equal to tau, the voltage of the capacitor will be equal to 63 volts. On what factors does tau depend? We are going to discover in the following experiment. This experiment shows the charging process of a capacitor. In this circuit, we have a resistor, a capacitor connected in series with a generator. In this simulation, I can change the value of the resistance of the resistor R and the value of the capacitance of the capacitor C. The experiment that I'm going to do is that I'm going to change the resistance and I'm going to change the capacitance, and in each case I'm going to see how does these values affect the time tau. How can I see or record time tau? The time tau is recorded in this case by the graphs at this point. Notice that this point has an abscissa which is equal to tau and ordinate which is equal to 63% of Q or of U. For example, in this case, when the capacitance is equal to 2 and the resistance is equal to R, notice that tau in this case is equal to 2 seconds. Then the capacitor in this case, for this value of R and for this value of C, needs 2 seconds in order to charge 63% of its maximum voltage. First of all, I'm going to choose 1.2 for the resistance and 1.4 for the capacitance. This is 1.4. Close the switch and then record the time tau. I'm going to put the cursor here, and this cursor shows that time tau is equal to 1.7 seconds, as you can see here. And also I can see it from this graph, which shows the current as a function of time. it is also 1.7 seconds. Now I'm going to increase the resistance until it reaches 1.5, and I'm going to keep the capacitance as 1.4 and then close the switch. See that the graph of Q as a function of time is increasing, and the graph showing I as a function of time is decreasing. Now we are going to record time tau. In this case, when we change the value of the resistance, time tau, as you can see, it is equal to 2.1, then it is increasing with the increase of R. I'm going now to keep R 1.5, but I'm going to increase C until it reaches 1.7 microfarad. Close the switch another time, then record the value of tau. As we said, we can see the value of tau from this graph or from this graph. Notice here that the value of tau is equal to 2.6. So, when we increase C, tau also increases. Now I'm going to increase R till it reaches 2 mega ohm and the capacitance till it reaches also 2 microfarad. Close the switch and then record the value of tau again. In the three previous values that we have seen, tau is increasing with the increase of R or of C. Now I've increased R and C together. We are going to see what happens to the value of tau. Tau also increases, and in this case it is equal to 4 seconds. Notice that as we were performing this experiment, the time which is the total time which is needed by the capacitor to be fully charged was also increasing. So the values which we have recorded in the previous experiment are shown in this table. We've concluded that as R increases and as C increases, tau, which is the time needed by the capacitor to charge 63% of its maximum voltage, also increases. And we have seen that as R and C increase, then the time which is needed by the capacitor to be practically fully charged also increases. Then our conclusion is the time needed for the capacitor to be practically fully charged or discharged increases with the increase of R and C. So we know now that tau is the time needed to perform 63% of the charging or discharging process. What is new about tau now is that tau is equal to R times C, because tau, R and C are three proportional variables. So, at time t is equal to tau, the capacitor charges 63% of its maximum voltage, then UC is equal to 0.63 multiplied by E. 0.63 is 63 divided by 100. And at time t is equal to 5 tau, or when the capacitor is practically fully charged, the capacitor charges 99% of its maximum voltage, then UC is equal to 0.99E, which is approximately equal to E. What about the current? At time t is equal to tau, the current in the circuit loses 63% of its maximum value, then the value of the current is I is equal to I0, which is the initial maximum value, minus 0.63. I0, which is the value lost by the current during the charging process, and at time t equals tau, and if we subtract these two, then it will give 0.37 I0. Then we can say that at time t is equal to tau, the value of the current inside the circuit is equal to 0.37 I0. At time t is equal to 5 tau, the current in the circuit is approximately equal to 0, and I is equal to 0. This graph shows two curves. This curve, which the one in pink, shows the variation of UC. You can see that this is an exponential function, increasing function starting from 0 and reaching the full charge or the full voltage at time t is equal to 5 tau, which is approximately 99% of the maximum voltage. And we can see that at time t is equal to tau, the capacitor will have a charge which is equal to 63% of the maximum charge. The other curve, which is this one in blue, shows the variation of I. We can see that this is an exponential function decreasing from the maximum current, which is at time t equal to 0, and decreases towards 0 at time t is equal to 5 tau, where practically the capacitor is fully charged. And we know that at time t is equal to tau, the current has a value which is 37% of its maximum value. Application number 4. A capacitor of capacitance C is charged by a battery of constant voltage E through a resistor of resistance R is equal to 10 kilo ohm. The adjacent figure shows the variation as a function of time of the voltage across the capacitor. Answer the following questions using, if possible, the adjacent graph. Part 1. Determine the voltage of the battery. Part 1. When the capacitor is fully charged, then UC is equal to E, which is equal to 3 volts. That is shown by this figure, that at time t is equal to 5 tau, or at the end of the charging process, the charge of the capacitor is equal to 3 volts. Then it is equal to the voltage of the battery. Part 2. Pick out the time constant of the time of the circuit RC. The time constant tau is the abscissa of the ordinate UC, which is equal to 0.63 E. First of all, we have to calculate UC. Then we have to multiply 0.63 times E. What is E? We have said that it is equal to 3. It will give 1.89. Then we are going to go to the graph and see what is the ordinate of this point. 1.89, which is approximately equal to 2, or 1.9, then tau is equal to 2 seconds. This is the point that we are talking about. This is the abscissa, which is tau, which is equal to 2 seconds, and this is the ordinate, which is approximately equal to 1.9. Part 3, we have to deduce C. We have to use the relation tau is equal to R times C. So C is equal to tau divided by R, which is equal to 2 divided by 1/10,000, then it is equal to 2 times 10 to the power minus 4 farad. In part 4, find at time t is equal to 3 seconds the voltage of the capacitor, the intensity of the current in the circuit, and the stored electric energy. First of all, how do we find UC? Simply from the graph. We have to look at time t is equal to 3 seconds. What is the value of the voltage across the capacitor? It is approximately equal to 2.4 volts. Then, to find the voltage of the capacitor, to find the intensity of the current in the circuit, we have to use the law of addition of voltages in series connections. E is equal to UC plus UR, then E is equal to UC plus RI. According to Ohm's law, we have substituted UR with RI. Then I will be equal to E minus UC divided by R, which will give 6 times 10 to the power minus 5 amperes. The stored electric energy at this instant is equal to W is equal to half Cu squared. Here it is UC, which is the voltage of the capacitor at this instant, which is 3 seconds. Then it will give 5.76 times 10 to the power minus 4 joule. You are going to discover more about capacitors in the other videos. Thank you for watching.